Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be starting our new chapter looking at pretty much atomic structure. So in order to start this off, we're really going to start in kind of an odd place by looking at the properties of light. And one of the reasons why we're going to be doing this is because it turns out when we're trying to understand chemistry, really what we're looking at is the behavior of atoms and molecules. However, one of the key features that we're going to explore a lot later is that all molecules are held together by electronic interactions. Most specifically, we've got electrons suspended in between nuclei, and we really need to understand the behavior of these electrons. And in order to do this, we need to first know where the electrons are and how they end up interacting. Now, in order to understand the behavior of electrons, we need something that can measure a small charged particle. And so really how we look at the behavior of these electrons is by using what are called spectroscopic techniques, which literally can be translated as measurements, scopic, using light, spectro. So we're going to be measuring things using light. And so in order to understand electrons, which will help us understand molecules, we first have to look at the behavior of light itself. So once we understand how light behaves, we can use this to determine the location and behavior of electrons around simple atoms, and then we can expand these towards molecular systems. So let's go ahead and talk about what the heck light is. So one of the key features is that light is essentially a photon, which is a really small particle that moves in a forward direction by causing changes in what are called electric and magnetic fields. So it turns out that electric is a way of looking at charges, and magnetism is essentially related to the movement of electric charges. So if I have a charged particle sitting, say, somewhere here in space, and a photon comes by, what we really do then is we have this oscillation in the charge field, which more or less makes that charge move a little. So you can cause charged particles to move by shooting photons at them. You can make them move a little bit more or a little bit less, depending on how things are set up. So as a photon goes by, it can essentially cause all of our charge systems to move by oscillating that electric and magnetic field. Conversely, if you have a charged particle moving, just like if I'm splashing an object in water, you can actually generate a photon by causing an oscillation in that electromagnetic field. So how can we go ahead and measure how these waves move through? So we're going to use several key properties. So we're going to go ahead and look at how this electromagnetic field changes essentially in location. So one of the easiest ways you can do this is by measuring, first of all, the wavelength. So this is essentially how the distance that causes it from one point in the wave to the exact same point. So for example, if I had a charged particle, if I'm here, it won't interact with the photon at all because there is no oscillation in the charge. If I'm here, we'd have a slight increase in the charge. If I'm here, we'd have a slight decrease. But you'll notice that there's 2 points at which there's no movement. These are called nodes. And you're essentially going to have 2 nodes for a single wavelength, one at the very beginning and one in the middle. You may say, hey, wait a minute, there's a node right here. But here's the big feature of waves, that this point is the exact same as this point, because this is where we start, this is where we end, which means this is also where we start, because every beginning is some other beginning's end. So that's a key feature with trying to look at how waves move. However, one of the big things is that we don't just have this oscillation in the electric field. We have to remember that these photons move in a given direction. So they're moving this way. So that means that if I wait a split second, then suddenly what we're going to see is that the node isn't here, it's going to be somewhere here. So a much more common technique is you go ahead and look at a given point and you see how many times in 1 second I end up having this wave pass by. This can often be measured by seeing how many times that peak intensity goes through a given point. And so you can often measure this via a set of different techniques. However, it turns out that the wavelength and the frequency of a wave are going to be related. And it works out that this is going to be related whether or not you're looking at a photon or an actual ocean wave. Because if you know essentially how long the wave is and its speed, you can go ahead and figure out the frequency. Because if I know how many waves hit per second and the size of the wave, I know essentially how fast that wave is moving. So the speed of any particle that generates a wave can be determined by multiplying its wavelength times its frequency. However, this is where a very fun peculiarity that works only for light comes into play. It's the speed of light is always the same. The speed of light, often denoted as c, which we'll see several times coming forward, is about 3 times 10 to the 8th meters per second. And this provides a very cool feature that since the speed of light is fixed, this means we have a fixed relationship in between the wavelength, or the distance between crest of a wave, and its frequency. So I can measure the wavelength as the inverse of a measured frequency. So as long as you know one value, you know the other. So if you start with the frequency, you can produce the wavelength. You start with the wavelength, you can produce the frequency. This inverse relationship also has a very kind of cool feature. It means that if I have a very small wavelength of light, it means it's moving very fast. I have lots of waves hitting. So again, the smaller the wave, the more waves have to hit for a given amount of time in order to keep that speed constant. Now, this can actually plays major roles in our everyday life, because what it means is that if I've got a longer wavelength of light, then essentially it means that it's going to, I'm going to have fewer, I'm going to have a lower frequency. And as we're going to see later, lower frequencies end up requiring less energy. And if I've got that longer wavelength of light, it makes it easier for the wave to pass through different objects. So long wavelengths, you can pass through more objects, less energy to produce. And this comes into major play in our everyday life because it turns out radio waves are actually light. And so let's go ahead and take a look at our local student radio station. It is 88.7, which it turns out those numbers on FM radio refer to the frequency of light. So for example, our local radio station has a frequency of 88.7 megahertz. So what's going to be the wavelength of that spectrum? So we can say, all right, wavelength is going to be our speed of light over frequency. So then we just have to plug in numbers. Big thing to watch here is that megahertz is going to be 10 to the 6th hertz. So we're going to want to go ahead and convert to make sure our units cancel out. So now we've got meters per second over per second. We're going to be left with as units of meters. So it turns out the wavelength of our local radio station is about 3.4 meters. And you might say, why do I care? Well, this means that in order to generate or receive this radio station, you have to have an antenna that's some integer of at least half that wavelength. Because in order to get a wave to fit on an object, you have to make sure that it can take a wavelength. And so this is a key feature of when you're fiddling with the knob on your radio, what you're actually doing is changing the length of your antenna to figure out which wavelengths it will receive and thus which frequencies. So the radio station transmitter and a receiver have to be some integer of half of the wavelength. So for example, the minimum length of wire you need in order to receive the local student radio station is almost 2 meters long. So that's a fair bit of length. So it would be about 5 5 feet. And we can apply these general rules to anything on the electromagnetic spectrum. And so this goes all the way down from very low frequency light, like radio, to microwaves, which turns out can be used to cook your food or to transmit information on your cell phone. Infrared, which it turns out that people generate naturally through our body heat. And then, of course, the visible spectrum. You'll note that the light you think of every day is only a small portion of the whole electromagnetic spectrum. Then we've got ultraviolet light, which essentially ends up being the light produced by sun that can give you cancer. X-rays, which everybody knows, and gamma rays, which will also be much more likely to give you cancer than superpowers. So generally, one of the other big things we have to keep in mind about light is that the energy of a light is going to be really dominated by the wavelength. However, the brightness is determined by exactly how many photons are essentially coming through. This can also be measured as the amplitude of our electromagnetic radiation. And you can control the amplitude by bending together different light sources. So let's go ahead and say that I bring in 2 different photons of the exact same wavelength in phase. Well, this means that this photon gets along with this photon. So I'm going to have a much brighter light source. So this would be having 2 people slap their hands on water at the exact same time, and you produce a much bigger wave. However, if these slaps occur just slightly out of phase, it means that this photon is going to try and generate a positive direction, while this one generates a negative. And if you get it just wrong, you get no waves at all because they annihilate. So this is a big feature, making note that light can either be additive or subtractive. So they can add or annihilate. And this is a major feature in a very common application these days, lasers. How essentially lasers work is you go ahead and you feed in a light source of only a single wavelength. So if you ever take a look at a laser, usually it will say exactly what wavelength the laser is. And you go ahead and keep feeding in photons of that exact same wavelength, and they bounce back and forth in what's called an optical cavity. And they keep getting bigger and bigger, making it brighter and brighter. And then you let a little bit of that light out, and what you get is a laser. It's a single wavelength of light with a very large amplitude. And this is only possible if you know the basic concepts of how light and electromagnetic spectrum works. So next time, we're going to go ahead and take these principles of light and try and use it to determine a little bit about the behavior of electrons. Until then, take care.